Assalamu alaikum. My name is Sharjil Ahmed, and now I give a short description, short presentation of TLC, Obe Assignment. So, uh, in modern healthcare system, efficient monitoring of ICU bed occupying is essential. This project presents a digital system that monitors patients' admission and discharge in real time and indicate whether the ICU bed is full or empty or someone discharged or someone in. So this monitoring, we can monitor this. The system utilizes digital logic components such as counters, D flip-flops, timer, and finite state. We're using here D flip-flop. Uh, and it is developed to assist hospital staff in making fast and accurate decisions regarding patient placement and resource management. So this is my ID. Now maximum ICU capacity. So what is the maximum ICU capacity? So in the question there is a given instruction. So according to this instruction, according to my ID, so this is the ICU bed capacity, and that is 8. Now this is what is it? This is block diagram. We use a 4-bit synchronous up down counter here, and then there is a flow chart of the system. This start initials counter, then go. There is the flow chart. Then we design the circuit. So here we use 4-bit uh, 4-bit D flip-flop. Why we use D flip-flop? Because D flip-flop is useful, better than JK flip-flop. It has just one input, and it is useful, and uh, it is good. It is good. It is better than JK flip-flop in design. So we use D flip-flop. And why it is 4-bit? Because the IC bit capacity is 8, so we need to count from 0, 1, 2, 3, 0 to 8. So if we count from 0 to 7, then that is we can design in 3-bit, but here we count from 0 to 8, so that's why we use 4-bit up down synchronous counter. And and here we see that the clock is shared, every flip-flop it shared the same clock, so we can see this is a synchronous counter uh, because the clock is shared here. Why we share use synchronous counter? Because in synchronous counter it reduce the propagation delay, so that's why we use it. So just do up and down counter. So when 100 occur, then it again reset to its uh, previous state. So that's it work. Then this is the equations of this, and this is how the system is work. Then move on to the number 2 question here. So there is a given instruction P according to the question and my ID, and this is 48. So there is a instruction given that if uh, the value of P is higher, sorry, this is the instruction. If the value of P is more than 50%, then we just then we just then when we calculate the duty cycle, we just do the duty cycle. And if it's not, then we uh, decrease from 100 minus P, the value of P, then we found the duty cycle. So here it is 48, so it's obviously less than 50. So here we just subtract D equal to 100 minus P, there is 48 and equal to 52%. So my duty cycle is 52%. Now we count the frequency. So it's also according to instruction, and it is 12. Then we get timer or time period, that is 1 by frequency, and that is 83.3 millisecond. So now we need to get higher timer and lower timer. So higher is we know that duty cycle into the timer equal to timer higher, and for lower we just calculate total timer minus higher timer, or we also do this we instead this we also do that 0.48 the remaining duty cycle into that, also get the same answer. So then choose capacitor is 50 macrofarad, then the equation higher lower the equation, then we just calculate its complex calculate this, and then we get RB. So RB we find 1157 ohm, then we just convert it to kilo ohm, and we get 1.1 because it is the standard value that found in store or shop. So we calculate 1.1 kilo ohm is RB value. Then for RA value we calculate we get it 90 ohm, but for standard we use 100. Then there are full display. So full display does not flash, so it remains stable, and we know that if it does not flash, it does not blink, and it is just 1 point, then if someone toggle then it changes it, and then again toggle, that is, so that is monostable mode. So here we just draw the diagram of monostable mode, and if it is stable, and stable mode is just it's blink continuously, blink out, blink like the traffic traffic signal, it's blink and blink out. So this is stable mode, and this is monostable because it doesn't blink, it needs to toggle to change its then we do here. So and this is stable, this is the circuit diagram of stable. And what is the main difference here? There are main difference is it has more resistance than monostable. It has just one resistance less compared to this stable. So just draw it, and the 555 timer we here looks a built-in enable pin to hold an output. Combinational logic must be used to provide smooth operation and control the output from the digital combination. Also we just use a buffer to VCC and output from the digital comparator acts as on stable signal. We feed the count equal to 12 signals and timer 12 equals to frequency, and output and gets it from the full display. That ensures the display perfectly toggle based on the sensor count without signal interference. So this is our triple five timer. Now move on number 3. So number 3 there is given that we were a FSM design that outputs a for here is the condition here, if TS is greater than 4 and TL is greater than 4, then we say it is 4 and it is 4. So from this we get TH and TL from here, from number 2, and they are obviously more than 4, so we set it 4. Then clock period is 1 millisecond, that also given in the instruction. Now according to this we this is a FSM you call it a system diagram. So here is all input comes, clock, reset, it's all our inputs, and their outputs A and B. So two outputs here. Now this is state diagram. If 0000 that can go reset, then 001 if it is on means it's go, then it's 001, then 0010, then it's continuous to this cycle, and it is continue and it's continue until someone press the reset. Then this is the state table. So this is reset and one, then it's present state, it's all present state, then it's next state, then output here, just two output A and B. So this is the table. Then from this table we can get ns not ns1, then two output, from two output A and B, A and B. So we get this equation, and from the equation we get our HDL code. So first we appoint our outputs here, then sorry input here, then output to output A and B, then we assign A for output A in this way, and assign B. So this sign is means negative, and this is and this is OR. So according to this, so you do the code and in the module. So this is our HDL code is end. So and final the question is says what is the drawback and limitations of 1 and 2 part. So so here are drawbacks and limitations. So what is the drawback? The current system has a 4-bit counter, so it is a massive drawback, because a 4-bit counter we cannot upgrade the system later. It just carry for 0 to 15. So if we need to upgrade more than 15 patients, or we just in future we just upgrade the hospital ward, so we cannot do that. So for that this is the limitation. And here we said if the ward is upgraded to hold more than 15 patients, this 4 bits counter will not enough. So it is not enough, so it resets to 0, and it breaking the system. Sensor based counter may produce false counts. Also sensor based counter also may produce false counts. Small disturbance or repeated triggering can increase or decrease the count incorrectly. Then proper debouncing is needed for reliable operation. Then the 555 timer output depends on resistor and capacitor tolerance. So frequency and duty cycle may slightly vary, and additional logic gates are required to control the system, increasing circuit complexity. It will increase the circuit complexity. So what is the modification for higher capacity? So we just replace the 4-bit counter to a higher bit, like 8-bit or more, so that this is future proof, we can upgrade it later. And use a multiple 7-segment display with BCD counters for displaying larger numbers. Add proper debouncing and improve control logic for reliable sensor operation. So what is the impact of it? So if we use more circuits, more gates, more with that this complex the hardware, so and also it increase the cost. So there's hardware complexity and manufacturing cost will increase, because more flip-flop needed, more gates needed, more display are needed. So this can obviously hardware creates hardware complexity and increase the cost. Then there is a slightly propagation delays increase due to additional logic gates. So the system eventually need to shift from a logic and 555 timer to a microcontroller or DSP based design. DSP means digital signal processing, and microcontroller that is a small programmable computer chip used to control electric system automatically. That in microcontroller we need less capacity, and it work more complex and need less hardware complexity. So we can do this. So this is it. So this is our topic, our full presentation of this assignment. So thank you.